So we're going to look at the exercises from problem set 6. So these are starting on page 6. So we start with number 10, which asks us to draw a Lewis structure for NH3, which you've already done up in table 1. That looks like this. And then it says how many electron domains. So electron domains is the same thing as electron groups, just another word for it. So if we look at the molecule, we see that we have 1, 2, 3, 4 electron groups, right? 4 electron groups. Now, if we want to make a sketch of this, there's a few different ways we can go about doing it. But the first thing that we need to realize is 4 electron groups means that the electron group geometry or the electron domain geometry is going to be tetrahedral. Right, which means it's going to be derived from that shape. Now, one of the ways that we can show this is like this. Now, if you're struggling to draw in 3D, if you have your model kit, use it. If you don't, remember that link I sent you to the PhET simulation. And then to show the lone pairs, which take up space, there's a few things you can do. You can just kind of make a little bubble thing like that. That probably does a good trick. That's good enough for this. Now, if we look, and then, so the drawing of the sketch for water in figure 2, and we want to make something similar. So really, it's kind of the same picture, just done a little bit differently in that sense. And remember, because we're dealing in 3 dimensions here, the angles there's a lot of different ways in which we can represent each of these molecules. This is one way I could easily represent it. Maybe something like this as well. Now, the thing is, in general, when we're drawing in 3 dimensions, we don't have to show electron pairs, and that's why we differentiate between, say, this version and this version. But one of the things I want you to actually get used to is, especially in the cases of nitrogen and oxygen, show the lone pairs. You don't need to show a bubble or anything like that, but show the lone pairs. And this is because as we go forward, those electrons are going to do stuff. And so the geometry and the chemistry, the reactivity that comes from those lone pairs all come together. And it's really important that we remember that they're there. Also, they can be a visual cue for you to remember why did I draw something the way I did. And the shape, so the electron group geometry is tetrahedral, but the molecular geometry, which remember is kind of what we observe this molecule, the electron geometry is going to be, I'm going to type this because I can't write very well, right? So the electron group geometry is tetrahedral. Molecular geometry is, in this case, trigonal pyramidal. All right. And the bond angles are going to be, right, in this case, this is one of the ones that actually I expect you to know. The derivative, the parent shape, tetrahedral, has bond angles of 109.5. In ammonia, the bond angle is 107. All right, now we're going to move on and do the same thing for, in the next question, the same thing for methane. So that's question 11, and it's CH4, right? And now if we look at the Lewis diagram for CH4, it looks like this. And again, this one here has 4 electron groups. Right? This one has 4 electron groups, which means that it is also tetrahedral. Just going to write tet. Okay. Now in this case, they're all bonding groups, right? So that means that the electron geometry and the molecular geometry are the same. And in 3 dimensions, it looks something like this. And the bond angle here, if you recall now, is 109.5 degrees. All right, number 12. Now we have SO2. So here we might have to try a little harder with our Lewis diagram. So SO2 has a electron configuration. It's the same as oxygen. So that means 2 non-bonding pairs and 2 bonds. And then we put in our oxygen atoms, right? And now if we put 2, 3, 4, and then this, da, 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 da. That should do the trick. Now, clearly, this is not going to really work because we've got the problem of these unpaired electrons. So we have one possibility of just pairing all of those up. So we get something that looks like this. Now, if we evaluate this Lewis diagram, we can see clearly that while it's okay for the oxygens, the sulfur has an expanded octet now. Again, you should remember that this is one of those things that's a little bit in between in terms of what's acceptable and what's not. So this is fine, and it turns out conveniently that even if we want to make another version of this, so another version of this Lewis diagram that should solve our problem is this one here. Now, again, there's some contention about which one of these would be better. In this case, we have the oxygen is -1 and the sulfur, 1, 2, 3, 4, 5, the sulfur is +1. The total formal charge is 0 in both cases. Now, if we think that we prefer to not have the expanded octet, this is better. If we're looking for lower formal charges, this one's better. In reality, both of them are neither of them really is entirely correct. And for our purposes, we're going to kind of accept both of these as possible answers, and they should both have the same geometry, because in either case, they both have 3 electron groups on the sulfur, right? 1, 2, 3, so that's 3 electron groups. Or over here, we still have 1, 2, 3 electron groups. So it doesn't really matter. And 3 electron groups means that the parent shape is trigonal planar, right? So 3 electron group But we can see that, in fact, it's two bonding groups and one non-bonding. So it's going to be trigonal planar but bent. So we're going to draw it something like this. And so our electron domain picture, or our electron group geometry picture, is going to look like this. And then if we wanted to draw the shape, so it's going to be the molecular geometry. And again, in the case of the molecular geometry, we don't need to show any lone pairs. I often show lone pairs on central atoms because it reminds me why we're doing something, why I chose that shape, but it's not required. So the molecular geometry in this place is bent. And the bond angle here is going to be less than 120. All right, now this brings us to question 13. All right. So we're going to look at all of these molecules, and we're going to draw Lewis diagrams, and we're going to draw them in 3D and look at their geometry. So the first one is pH3. Now remember, phosphorus has the same electron configuration, valence electron configuration anyway, as nitrogen. So it's going to look like this as a Lewis diagram. And then there are 4 electron groups, so it's going to be tetrahedral, but there's 3 bonding and 1 electron, or 1 non-bonding, so it's going to be trigonal pyramidal, like that, right? So, and the bond angle here, we don't know what it's going to be, but we know that the angle is going to be less than 109.5. And so this is here, the electron group geometry is tetrahedral. And the molecular geometry is going to be trigonal. Next is CO2. That one should be straightforward. CO2, which looks like this. And in fact, really, the Lewis diagram, if we draw it reasonably well, this looks exactly like what we drew before. And the bond angle is going to be 180. And the electron geometry and the molecular geometry are linear. Next, SO3. SO3 has a Lewis diagram that looks like, let's see. We start with this, right? And obviously it's not going to be like this because of all the lone pairs, all the unpaired electrons rather. So what we are going to do is try and pair some stuff up, and SO3 ends up being a bit of a funny one because it's very hard to explain. One of the ways we can draw it is like this. Now, irritatingly, SO3 can be an odd electron species, and in fact, the best probable way to draw SO3 is if we go with sort of the expanded octet version, right? We can have this. Alternatively, we could have this version here, where the sulfur is going to be 2 plus and these oxygens will each be minus. Both of these are acceptable, and conveniently they have the same geometry. So they're both, so in this case, again, there's no electron groups, so the electron geometry and the molecular geometry are both trigonal planar. SO3 minus 2 So in this case, we're going to have 2 extra electrons. So really, it's going to look like this. Is one possibility. Like that, so minus. Alternatively, we could have it drawn like this. And again, just like in the other cases, the two geometries will be the same. These are the Lewis diagrams still, right? And in this case, so each of the oxygens is negative and the sulfur is plus 1. So there are 4 electron groups in this case, right? So that makes it tetrahedral. So, but it's going to be trigonal pyramidal, so something like, again, a bit like NH3 or pH3, like that. Right, and if we want to show the electron domain, we would do that. If we want to show it in 3D, just the molecular geometry, we would show just that. And this is the molecular geometry is again trigonal pyramidal. All right. Now, honestly, the next two are N2 and HF. Now, both of these, right, if we look at them, the Lewis diagrams are like this, and like this. And in these cases, it's a bit of a trick question because really there's no geometry to consider. So we can honestly just skip over those, right? We really only are worried about shape when we have atoms bonded to more than one other atom. So after this comes hydronium H3O plus. So the Lewis diagram here is like this, right? We have the oxygen, 3 bonds, and a lone pair. Looks like that. And that's it. So again, this is going to be derived from a tetrahedron because there are 4 electron groups. So we're going to draw it, again, exactly like those other ones we just looked at. So something like that. And then if we're going to draw it as the molecular geometry, which is really the more common way of drawing things, we're going to draw it like that. And I often put in the lone pairs out of habit more than anything else, but I don't put any bubble. So in this case, the electron geometry is molecular geometry is, again, trigonal. All right, next coming is the, what is that? NH2F. So NH2F is going to be the same as ammonia, same as NH3. So the Lewis diagram is going to look like this. And so that means that, right, the electron geometry is going to be tetrahedral. Molecular geometry is going to be trigonal. Pyramidal. And so what is that going to look like is, well, exactly like everything else we've drawn essentially so far. So if I show it with the electrons, it might look something like this, like with the what we call the electron domain, right? So we might put in a bubble, or we might not, and just draw it like that. CCl4 is really the same as CH3 rather, right? So it's going to be the Lewis diagram with, it's going to look like this, right? Oh, forgot some. And this time it's just going to be tetrahedral because there are no electron pairs. So something like that. And in this case, the electron geometry is, and molecular geometry are tetrahedral. We're going to skip O2 because We're going to skip O2 because honestly, it doesn't really matter. There's no geometry to O2. But if we go over to ozone, so O3, we've seen this structure before. The Lewis diagram looks like this, right, where we have a plus and a minus. And so there's 3 electron groups, so it's going to look like this. And I've left out some of the bond angles in the other structures, but you can go back and add them in. Now, you might be tempted. Actually, in this case, it's pretty straightforward. Sorry. So it looks something like that. And the bond angle here is going to be less than 120. So we can draw it like that with our bubble, or more preferably, we're going to draw it just like this. And there we go. Carbonate's another one we've seen, and we need to be careful with molecules like carbonate. I was getting a little bit ahead of myself before. That's why I started thinking about this. So carbonate, right? Now, if we draw the Lewis diagram for carbonate, we know, right, just as a Lewis diagram, it looks like this. There's no lone pairs. I forgot, just if we go back here, right, the electron geometry is trigonal planar, and the molecular geometry is bent. Now, if we go here, the temptation, now this is the Lewis diagram. This actually works really well as the, and sorry, this is, each of these is negative, right? This works as the 3-dimensional drawing. And the temptation here is to say, oh, look, I've got a double bond and 2 single bonds. So these are shrunk, right? This angle here is going to be decreased. But you have to remember that the geometry is really much more related to the resonance hybrid. And in this case of resonance, all of the bonds are equivalent, right? If you remember in the case of carbonate, the diagram looks, the hybrid looks like this, right? And so in this case, the bond angles are all going to be 120. They're going to be equivalent. And the electron geometry and the molecular geometry are going to be trigonal planar. So the last one in this bunch is formaldehyde. And in this case, actually, the bond angle here will be less than 120, and this one will be greater than 120 because there's no resonance here. There actually is a double bond and 2 single bonds, and there's more repulsion there. So in this case, both the electron geometry and the molecular geometry are still trigonal planar. Right, that was a lot. That was question 13. Moving on to question 14. The question is, why is it that in this molecule from our table, why is it that the bond angle here, the HCC bond angle, so that's this angle, why is it 180 degrees? And in this case, it's pretty straightforward. The carbon atom is bonded to 2 other groups. So the furthest away they can be from each other is 180 degrees. That's pretty straightforward. If we go to question 15, which is about this molecule here. All right, and again, this is one from table 1. Question is, why is this bond angle about 117 degrees? Well, the reason is that, remember, lone pairs repel more than bonding pairs. So the lone pair squeezes the other two bonding pairs toward each other. And that's really it. That's the whole reason. All right, question number 16. So the question is, and I will just show you the molecule again, just so you remember. So we want to draw glycine in 3D. Here's the molecule of glycine, and what we want to do in the case of glycine is every time when we have these more complex molecules, what we actually need to do is draw each sort of atom independently when we consider its geometry. So if we look at it, the nitrogen atom here is going to be trigonal pyramidal, right? This is going to be tetrahedral because there's 4 things. This carbon atom has 3 things, so it's trigonal planar, and this one is going to be bent. Now, when we get to more complex molecules, one of the things that you really want to try and do is make basically what we're going to call a backbone for the molecule. We want to get as much of the molecule in the plane of the page. It just makes drawing so much easier. So we want to get as many atoms in the plane of the page as possible. And this here at the very minimum is our backbone of the molecule. If we can throw in some of the hydrogens to make our lives a little bit easier, that will be even better. So what we're going to try and do here is see if we can get all of these atoms in the plane of the page. And it really shouldn't be too much of a problem. For example, if I start, it might not seem obvious, but if I start with this carbon atom here, right, this carbon atom is trigonal planar, right? It's flat. So if I draw the geometry of this carbon atom, it looks something like this, right? So that works really well, actually, because it gets me my next carbon in the plane of the page. Now, drawing tetrahedral carbon atoms is not always obvious. And again, if you have a model kit, super. If you don't, it's one of those tricky things. I'm just going to open up it's not going to show, actually, unfortunately. But one of the things we know is when we draw a tetrahedron, there's 2 bonds in the plane of the page, and then one coming out and one going back generally. So I'm going to sort of put this one here this would be to the nitrogen atom. And so then I would have 1 hydrogen down here coming out and 1 hydrogen down here going back. All right. And then I can draw for my nitrogen the same thing. Usually the easiest way is 2 bonds in the plane of the page, and then 1 coming out or going back. I'll draw it going out. It doesn't matter. And then this one's bent, and bent only has 2 bonds, so there you go. So that's what this molecule is going to look like. So there you go. Now for question 17, we have a more complicated case, but that's always more interesting. So we'll look at this and then we will talk. We'll look at this and then we'll go through. Now, one of the things to realize is that there's sometimes stuff missing from pictures like this, all right? One of the things that's missing in this case is some lone pairs, like on this oxygen atom right here, right? So I think it's a safe bet actually right here. Let's see how this looks. You can say all of these are trigonal planar. Right? And then so is this one. And then, so that whole part of the molecule is actually flat, right? If you connect a bunch of flat triangles, everything related to it is flat. This is going to be trigonal pyramidal, but still based on tetrahedral, and this one is bent based on tetrahedral. So we're going to grab this, we're going to shrink it down a little bit just to make my life, well, it doesn't look very good, but it'll have to do a little bit easier. Right. So if I want to draw this in 3 dimensions, most of the molecule actually looks exactly the same. This whole core, this whole ring cyclic part of the molecule really is unchanged. So it's a bit deceptive. Right? And same up through this, the carbon with the double bond to the oxygen, that's also unchanged. Even down the nitrogen, none of that has changed. And I can do this. All of these are, this is still, I mean, it's flat, but this is a 3-dimensional drawing. Right? And now this oxygen is bent, but it's tetrahedral bent, so again, the 2 bonds can be in the same page, plane of the page. The only difference then is here at the nitrogen where I have to have one of the bonds going out or going in the back. That's really the only difference for that one. All right. The next question is 18, and it's for acetic acid and acetate. So acetic acid, the Lewis diagram. Looks like that. And, oh, and it's the acetate ion. I apologize, not acetic acid. So acetate ion. All right. And in this case here, the HCC bond angle, well, this carbon is tetrahedral. So I'm going to expect that the bond angle is about 109.5. This one here, you have to be careful. There's a trick in here. Again, there's resonance between these 2 positions, right? Because I can draw this like this. So I'm going to expect that this bond angle is going to be maybe slightly larger than 120, but pretty close. So if I had to put my money on it, which I don't have the actual number, but I'm going to say this bond angle is going to be 109.5, and this bond angle is going to be maybe about or slightly bigger than 120. All right, number 19 is the last one we'll do. Number 20 is about the hydronium ion again, so we're not gonna break our heads and do that one again. So number 19 is a few different ones. So the first one is NO2 plus. Now NO2 plus is a bit of a weird one because we have to, NO2 plus. We have to drop some electrons here, right? So in this case, we have our nitrogen like this, 2 oxygens like this. Right? And we have to remove an electron, and we have to decide where to remove it from. And honestly, where we're going to remove it from is is from the nitrogen, because the nitrogen is the least electronegative element. So we're going to have this, and now we can see how everything connects up. So if I do these two like that, and then well, now I have to be careful, because if I make another double bond here, then the nitrogen is going to be hypervalent, and that's no good. So I'm going to move that nitrogen, the electron, over. So I'm going to end up with this. Uh, and like that. And what I actually have is this nitrogen atom is 2 plus, and the oxygen is minus 1. And so the whole thing works out to be 2 plus. Now, the interesting thing is that now, remember, 2 plus means there's missing stuff. There's nothing there. So the bond angle here is going to be 180 degrees, and it's going to be linear. The next one, N2O. So N2O. So this one looks like this. But this is one possibility. The other possibility for N2O is that actually it looks like this. These are the 2 resonance hybrids. In both cases, the central atom is positively charged. In this case here, we have a negative nitrogen. In this case, we have negative oxygen. Now, my tendency is to think that this structure here is slightly better because it has the lone pair on the oxygen, the extra lone pair on the oxygen, the negative charge on the oxygen. But that doesn't necessarily mean that that's really going to be the situation. It'll be a hybrid. But in both cases, the bond angle is still going to be 180, and it's going to be linear. All right, after that we have NO2Cl. So NO2Cl, NOOCl, right? This is going to look something like the nitrate ion. So we're going to have plus and minus. So the bond angle here is going to be around 120. Maybe not exactly. There is some resonance, and it will be trigonal planar. Last, but certainly not least, is NH2 minus. So in this case, the negative charge means there's going to be an extra lone pair on the nitrogen atom, right? And this shape is like water in essence. It's derivative of tetrahedral, so the bond angle here is going to be less than 109.5, probably less than 107 really, because of the repulsion. So there you go.